Okay, so a quick review of the soundness theorem. So it tells us that everything that we can prove is true. But what does this mean? It means that if gamma proves A, then gamma tautologically implies A, or more specifically, if A is a relative theorem dependent on gamma, then we know that gamma tautologically implies A. This is what soundness theorem says. And in the case that gamma is empty, for example, then we know that if A is an absolute theorem, then A is a tautology, or essentially every absolute theorem is a tautology, is what the soundness theorem says. So those are a number of different ways to think about what the soundness theorem says, and those are all helpful in the construction of our logic to ensure that it is in fact sound, that everything it proves is in fact true. So it doesn't prove anything that isn't true, which is really important. But as I mentioned before in the previous video, we're actually going to use soundness to help us prove fallacies. So in particular, to disprove particular well-formed formula, or to justify why a particular well-formed formula is not a relative or an absolute theorem. You may recall from 1019 that in order to disprove certain statements, you would actually construct counterexamples. And so we're going to see how soundness allows us to construct counterexamples to disprove certain statements. So in order to disprove a statement using soundness theorem, we're actually going to use the contrapositive of the soundness theorem. So recall that for a statement if P then Q, the contrapositive of such a statement is actually if not Q then not P. So in particular, the contrapositive of the soundness theorem says if gamma does not tautologically imply A, then gamma does not prove A. So to show that gamma does not prove A, it is enough to show that gamma does not tautologically imply A. Now recall, in particular, remember that gamma prove A is a theorem schema where A stands for any formula. So in particular, recall that in order to show this, so to apply the contrapositive of soundness, if we're trying to disprove a statement like this, our counterexample actually comes from this assumption here. So to show that A is not a theorem, we need to show that gamma does not tautologically imply A. But recall that this was also a schema, and so in order to show that this was not valid, we had to find an example of A, an example of the hypotheses in gamma, and then justify this statement by finding a state which satisfies all of the well-formed formula we have in gamma, but makes the example for A that we have false, right? So remember that we had to actually come up with examples for all of the well-formed formula within these statements, and that is where our counterexample comes from. So, for example, in order to show that A is not provable, or is not provable from gamma, or is not a theorem, then we need to find, we can find a specific formula for A and specific examples within our hypothesis gamma, and then some state that satisfies all of those hypotheses but makes A false. So essentially, to disprove any theorem, we find an example, a counterexample, and we justify this using our truth table arguments, which are much easier, right? So that is what is meant by a counterexample construction within our logic here. So to disprove a theorem, we find examples of the well-formed formula we're trying to disprove, and examples of the hypotheses, and then find a particular state which satisfies the hypotheses but makes the conclusion false. Okay, so that ends our study of soundness theorem here for the video, and we'll look at particular applications and constructions of counterexamples in class. Next, we're simply going to look at the completeness of our logic. And so recall, the completeness of our logic means that we can prove everything that is true. So formally, this statement was proven by Post, and so it's called post-tautology theorem, and it's in fact the converse of soundness. So it says that if gamma tautologically implies A, or if A is true or relatively true, then gamma can prove A. So we are going to use Post's theorem in class to prove logical equivalences, but at the same time you will see that this is a very important meta-theorem. In particular, if you do not like the proof methods we've been using and much prefer the truth table arguments, then here's a theorem which allows you to use the truth table arguments to prove certain well-formed formula. So, as an application, for example, if on the midterm I ask you to prove a particular well-formed formula and don't specify the type of proof method that you may use, then you can use Post's theorem and construct a truth table argument to show that gamma tautologically implies A, for example, and then applying Post's theorem, or completeness, you can justify that gamma proves A, and that will be enough. So this may be the best application for you, particularly if you prefer truth table arguments over the proofs that we have been constructing. Okay, so in class we'll go through other examples, and then we'll do some review to prepare you for the midterm in the next week.